while the globe buzzes with excitement over the all-clear signal for 3 Atlas, the third interstellar visitor ever recorded. Something far more disturbing is creeping along in the background, and we've only just caught on. A comet, bursting with erratic flares, is drifting perilously near Earth's path, closer than we'd ever want. It evaded our scopes until the sun's glow betrayed its position. Come October 20th, 2025, merely 8 days away, it'll hit its nearest point to our planet. What implications does that hold for folks down here? Is this the true peril? Stick around to the finish, and you'll discover why the genuine danger isn't the comet dominating the headlines, but the one that nearly escaped notice entirely. If these enigmas grip you like they do me, smash that like button and subscribe to catch every live development as events play out. Leave a comment sharing your location, the local time, and your take on whether we're hearing the complete story behind these game-changing finds. To boost this community, spread the word via X, Facebook, Reddit, or your personal chats. You folks make it possible for us to pursue tales like this. Thanks for your support. Let's dive into part 1, the bold headline assertion. Buzz everywhere centers on 3 Atlas. News outlets label it enigmatic. Social media explodes with speculation, while experts twist themselves into knots to calm fears, insisting it's harmless. They're spot on. This interstellar drifter from outside our solar system will sail by Earth at a safe 1.8 astronomical units, about 167 million kilometers. NASA states it clearly, zero risk. Its path remains distant, like a starry tourist passing through before fading into the cosmos. So what fuels the fixation? Its otherworldly origin. The term interstellar sparks a wonder that blinds us to the everyday. We adore the foreign arrival, the outsider knocking. We overlook intruders already inside. As attention fixates on 3 Atlas, a different body is sneaking into our cosmic turf. Comet C/2025 R2, named SWAN for the detection tool that revealed it, is drawing nearer. On October 20th, 2025, just 8 days out, it'll make its closest pass by Earth. Not 1.8 astronomical units, or even 1. Try 0.2606 astronomical units, around 39 million kilometers. That's nearer than it sounds. That's too intimate for unexpected callers. Let me outline this object's profile. R2 turned up in late September 2025, spotted by hobbyist astronomer Vladimir Bezugi, sifting through solar wind readings from the SOHO spacecraft's instrument. No telescope involved. He tracked glowing hydrogen bursts in UV light. That's an unusual comet hunting method. Typically, Earthbound optical scans patrol the heavens, snagging dim specks of sun-reflected light. Yet R2 dodged those. It lurked in the sun's radiant haze, too tightly aligned angularly for ground telescopes to detect. This is known as the Hulek blind spot effect, or Hulek, depending on the spelling, where items in that region turn phantom. They're there, yet undetectable until they break free. R2 surfaced only post-perihelion, its sun-closest mark on September 12, 2025. When we finally saw it, the comet was outbound, aiming our way. That perihelion sat at roughly 0.5 astronomical units, or 75 million kilometers from the sun, close enough to bake off icy layers, spark eruptions, and rattle its framework. And that's exactly what happened. Late September brought reports of a sharp surge in brightness. The comet spiked to magnitude 5.9 or 5.6 per varying accounts. Its coma, that hazy envelope of vapor and particles around the core, ballooned. Images captured a green-tinged aura, typical of fluorescing diatomic carbon and cyanogen radicals under solar UV. The tail spanned several degrees across the sky, catchable with binoculars if you pinpointed it right. But here's the kicker. The nucleus size remains a mystery. Its spin status? Unknown. Has it cracked, or might it? Comets are unpredictable creatures. They can flake off pieces, break apart, or scatter rubble trails in their wake. Should R2 fragment, those bits would veer off the main course just a touch. They'd disperse, creating a swarm that could cross Earth's path. The minimum orbit intersection distance, or MOID, between R2 and Earth clocks in at about 0.048 astronomical units, or 7 million kilometers. In space scales, that's razor thin. That's the divide between secure and potentially dicey, hinging on future developments. Look, I'm not claiming R2 will collide with us. Projections confirm it won't. But the core issue is our failure to detect it sooner. That's the actual hazard. Our monitoring setup excels at spotting things in ideal sky zones at optimal brightness hits at just the right moment. Yet if something lurks in the sun's blinding light or approaches from an unforeseen direction or flares up abruptly right after we've glanced elsewhere, it slips right by us. We overlooked R2 until it was nearly upon us. How many more have completely evaded detection? This isn't cause for alarm. Alarm serves no purpose. It's a call to focus on the threats that routinely dodge our gaze. It's about acknowledging that the most terrifying dangers aren't the flashy stories dominating the news. They're the hidden ones we only notice when it's far too late. The 3 Atlas setup is mere diversion. It's like the magician's flourish in the spotlight while the real sleight occurs offstage. R2 is that sleight of hand. So this is our plan. We'll first break down the 3-eyed Atlas diversion and explain why it's no real threat. Next, we'll delve into all the details we have and lack about R2. We'll examine the hypothetical danger paths, the debris streams, the chunks, the meteor showers. We'll stack this against previous close calls we scarcely detected, items that bypassed our safeguards with mere days or hours' notice. Finally, we'll cover what to monitor, what to push for from the agencies tasked with tracking these hazards, and the fallout when the spotting network glitches, which, believe it or not, happens more frequently than you'd guess. And in those breakdowns, the intruder that gets through often isn't the one you've been eyeing. Part 2. How it was found. Why did Swan pick it up when Earth-based scans didn't? Comets typically get picked up by visual sky sweeps. Scopes sweep the darkness for dim specks shifting against the starry backdrop. Those specks grow brighter nearing the sun. Their frozen surfaces turn to gas, sprouting tails. Humanity's been at this routine for ages. It's a solid approach until it isn't. Comet C/2025 R2 evaded optical scopes entirely. Instead, it turned up via a hydrogen glow sensor on a sun-circling probe. The device, SWAN, short for Solar Wind Anisotropies, rides along on the SOHO mission, the Solar and Heliospheric Observatory, which lifted off in 1995. SWAN's built to map solar wind patterns by picking up hydrogen Lyman alpha signals in the UV range. Hydrogen shines at a precise wavelength, 121.6 nanometers, unseen by our eyes, but vivid in ultraviolet. As comets vent water vapor via sublimation, it splits into hydrogen and oxygen. That hydrogen fans out into a vast haze encircling the comet, way bigger than the naked eye fuzzy head. From millions of kilometers off, SWAN can detect that haze even when ground scopes draw a blank. Nothing novel here. SOHO/SWAN has uncovered thousands of comets during its run, mostly tiny sun-skimming types that dive into the solar corona and evaporate. R2, though, isn't a sungrazer. It hails from the solar system's fringes, probably the Oort cloud, swinging in for a tight solar flyby before arcing back outward. What kept it off ground-based radars? Its spot in the sky. It hugged too near the sun's position. But the angle was minuscule. Earth telescopes can't stare straight at the sun without getting overwhelmed. A no-go wedge encircles the sun where stuff just drops out of sight. Experts dub it the Hill effect or the holeless blind zone, based on your favorite historical nod. The idea is identical regardless. Anything there becomes spectral. R2 navigated its closest solar approach right in that wedge. It looped around the sun on September 12, 2025, at about 0.5 astronomical units, roughly 75 million kilometers. For weeks prior and following, it stayed out of optical sight lines. Only after breaking from the dazzle did it show, already past perihelion and outbound into Earth's vicinity. That's when amateur skywatcher Vladimir Bezuki caught it in SWAN archives. He sifted through old UV images hunting for hydrogen's signature shimmer. He spotted a drifting patch, a hazy blob relocating across frames. He marked it for review. Peers verified. Visual backups confirmed. The comet checked out. But by that point, we'd squandered weeks of tracking. No records of its pre-perihelion antics. Zilch on its brightening curve, orbital shifts, or early breakup signs. Spotting delays act as harsh sieves. Visual sweeps face faintness thresholds, sky patch skips, cloudy disruptions, and dazzle barriers. UV hydrogen detectors like SWAN offer alternate picks, alternate gaps. They snag comets that visual instruments overlook, but they're no all-sky patrollers. Tailored gear nets tailored catches. Late finds carry heavy costs. Fewer data points mean shakier path predictions. Refining the route takes time, factoring in tugs, gauging drag from jets like venting gases. R2 was we overlooked its arrival. The path it followed remained unclear. Even after several weeks, uncertainties linger. We have a general sense of its trajectory, but approximations fall short of accuracy. In the realm of orbital dynamics, exactness matters above all. Moreover, we failed to catch the initial outbursts. Comets frequently erupt close to perihelion, where the sun's heat sparks the violent ejection of frozen gases. Should R2 have experienced this, it escaped our notice. We're unsure whether it released sizable debris during that phase. We lack knowledge of any fissures in its core. Its spin patterns remain unknown, influencing how it tumbles and twists amid uneven gas emissions. That data has vanished. We're navigating without guidance, attempting to forecast the actions of a body we began observing only midway through its performance. This isn't the fault of specific researchers. It stems from inherent flaws in our monitoring systems. Our setups prioritize particular object types in select sky regions. Anything deviating from those criteria slips by undetected. It stays hidden entirely until a hobbyist astronomer, equipped with satellite tools, spots a hydrogen shimmer in old records. How many more comets have evaded us? How many traverse the solar system at this moment? Unseen simply because they're positioned incorrectly at inopportune moments. The answers elude us. They always will. That's the core issue. Now, let's examine R2's developments post-detection. The flares, the peculiarities, the bizarre formations turning this comet into far more than a mere frozen boulder. Part 3. R2's actual activities. I'll guide you step by step through the sequence. On September 11, 2025, Vladimir Bezugi detected a shifting hydrogen signal in SWAN imagery. The body earned the label C/2025 R2, where R marks the half-month of spotting, and the 2 signifies it as the second such find in that interval. Visual verification followed swiftly. Earthbound watchers aimed their scopes at the given position and located it. A hazy spot, a coma shimmering softly in the early morning darkness. The comet had zipped past perihelion just prior, on September 12, at about 50,347 astronomical units from the Sun. That's proximity. Near enough to vaporize water ice, carbon dioxide, methane, ammonia, every gas locked in cometary makeup. Near enough to ignite processes. And processes stirred in late September. Spotters noted an abrupt surge in luminosity. The comet's visible brightness spiked. Certain calculations pegged it at 5.9 magnitude, others at 5.6. Since magnitude scales logarithmically, even minor shifts signal major glow-ups. The coma grew wider. Snapshots revealed a green aura encircling the nucleus. That's the hallmark of diatomic carbon fluorescing under UV rays. A staple in comets. Carbon materials vaporize off the core, solar rays ionize them, and they emit that eerie green. It appears otherworldly, yet it's pure science. The tail displayed imbalances. Certain photos captured streaks, thin spurts of matter arcing sunward. This points to focused emissions, likely from hotspots on the nucleus's exterior. Comets aren't even. They're mosaics of frost and stone, with zones varying in gas content. As the core turns, varied outlets face the sun, sparking activity waves. Consequently, the tail morphs, throbs, and occasionally divides into separate flows. R2 exhibited every bit of this. Watchers also observed substantial dust holdback. Typically, sunlight's push scatters fine particles, crafting a sleek tail. Yet if particles are hefty or clingy, they trail sluggishly, forming a hazy veil that disperses gradually. R2 appears to generate plenty of hefty particles. This carries weight. Bigger particles imply the core is sloughing off segments, perhaps shards, maybe slabs fracturing from heat strain. Should those segments prove substantial, they could persist as separate entities, each charting its course, potentially straying from the main body and scattering rubble through the void. A notably vivid photo surfaced on the Astronomy Picture of the Day site on September 18, 2025. It captured Artoo's green coma set against the dusk backdrop, tail arching skyward from the veiled sun's brightness. The comet hugged the horizon, challenging to track, yet impossible to miss. Sky imagers nabbed it, via binoculars or modest scopes. Accounts depict the tail spanning multiple degrees, a spectral band unfurling overhead. But here's the catch. Forecasting comet brilliance is infamously tricky. Comets defy straightforward patterns. They flare up. They dim. They break apart. Their shine hinges on the extent of sublimating surface, tied to core dimensions, makeup, spin, and sunlight exposure. We offer informed estimates, but comets thrive on defying expectations. Artoo is forecast to hit magnitude 4 in ideal circumstances. Predictions vary on the comet's brightness, with some forecasts indicating it could hit magnitude 3, making it plainly visible without aid from a clear night sky. More cautious estimates peg it at around magnitude 6, necessitating binoculars for spotting. By October 10, 2025, measurements show a magnitude of roughly 6.7, barely shy of what the unaided eye can pick out. Any further glow-up hinges on another outburst, though there's no certainty it will occur. The core stays indistinct. Observers through scopes only catch the coma, that hazy shroud of vapor and particles. The rocky heart lurks within, obscured and dim, impossible to isolate. Its dimensions remain a mystery. Guesses from luminosity and behavior point to a few kilometers across, but that's speculative. Shape? Unknown. Solid body or loose rubble pile? No clue. Has it already cracked? Certain comets break apart subtly, dropping fragments sans fanfare. You might spot it later via detailed imaging of the coma, revealing several dense spots or cores. Just a theory, but intriguing. The late September flare hints at volatile stores beneath the surface. Pressure mounted internally and burst forth dramatically. Perhaps carbon monoxide frost vaporizing in a rush. Or hidden water ice pockets hit by solar rays. Maybe even a structural snap, spewing fumes through a fissure. Regardless, it struck once. It might recur. Should it fragment badly timed, near our planet, the shards could form a scattered hazard stream that Earth plows into. Shifting to the data, solid orbital stats, ranges, velocities, the layout dictating if this sparks interest or worry. Part 4. Firm figures and trajectory assessment. Here's the setup. Comet C/2025 Artoo follows the Sun along a trajectory that's almost parabolic. Eccentricity clocks in at 0.9993699, darn near 1, yet not quite. Precisely 1 signals a parabola, an unbound path from endless space and back. A hair under means a vast, skinny ellipse, looping over tens of millennia. For Artoo, the semi-major axis spans about 798 Australian dollars. So its aphelion, the outermost reach, lies way past the Kuiper belt, plunging into the Oort cloud. The full cycle? Around 22,554 years. Last intersystem swing was in the late Paleolithic era, amid cave art and mammoth hunts. Orbital tilt sits at roughly 4.47 degrees. That's the slant of its path relative to the ecliptic, Earth's orbital flat. At 4.47 degrees, it's modest. Oort cloud visitors often slant steeply from odd directions. Artoo aligns closely with planetary paths. Easier to forecast, sure, but it lingers longer in the ecliptic zone where we circle, upping odds of brushes. Perihelion, Sun's nearest kiss, hit on September 12, 2025, at 0.50,347 Australian dollars. Some 75 million kilometers, grazing inside Venus's track. There, Sun's blaze is fierce. Ices turn to gas swiftly. Ices vaporize, stuff jets out. The core ejects particles wildly. This phase amps up shine, turns spectacles, but invites chaos. Now outbound, Artoo's route intersects our orbital lane. Closest Earth pass comes October 20th, 2025, at 0.26,065 Australian dollars, or about 38,925,170 kilometers, roughly 100 lunar distances. Feels distant in everyday scale, but astronomically, a close shave. Crucial metric, MOID, Minimum orbit intersection distance. The tiniest orbital separation, ignoring timing, pure geometry. R2's is 0.048 Australian dollars, near 7 million kilometers. Picture the path sketched. Closest point measures 7 million kilometers. That's the buffer. Wrong alignment could close it to nil. Yet timings differ. Solutions place Earth and R2 39 million kilometers apart on October 20th. It zips by harmlessly. Simulations confirm, math backs it. NASA skips alerts. No collision buzz. So what's the fuss? Paths aren't flawless. They stem from sightings, and sightings carry errors. More data refines the most accurate approach might be preferable, yet R2 was only identified relatively recently. We're working with a limited number of data points, short of what we'd ideally prefer. Its path is fairly solidly mapped out, though far from flawless. Minor disturbances, like non-gravitational effects from gas emissions, alterations in the comet's spin or material spread, could nudge its course by a small amount. A deviation of several thousand kilometers may be insignificant for the main body, but it becomes crucial if the comet has broken off chunks. Those fragments can veer apart. Should R2 be cracked or divided into segments, each segment would carry marginally varied speeds. Gradually, they'd fan out across the trajectory, creating a trail of rubble. Bigger pieces stray less, while tiny ones, dust specks, small rocks, disperse far and wide. Should Earth cross that rubble trail, we'd witness a surge in shooting stars, perhaps a full-blown meteor display, or even something more intense. As of October 10th, 2025, its glow measures 6.7 magnitude. That's fainter than forecasts indicated, but hardly unexpected. Comets dim as they retreat from solar warmth. The real uncertainty lies in whether R2 will surge with activity once more. A sudden flare-up would indicate fresh outbursts, potentially signaling breakup or fresh volatile ejections, which could drastically alter the hazard assessment. Picturing it clarifies things. Picture the Sun as the focal point. Our planet's path forms a near-circular loop around it, spanning about 150 million kilometers. R2 traces a prolonged oval, diving in from the solar system's fringes, looping near the Sun, then retreating outward. The paths cross, yet not simultaneously. The comet hits the crossing in October, while Earth follows suit several months afterward. This separation in space and time keeps us secure, for now. Comets defy easy prediction. They don't stick to rigid timetables. They sway, fracture, release debris, and those bits don't mirror the core object's route. They wander, disperse, and occasionally show up right when you don't anticipate them. Moving on, let's delve into the spectacle of watching it all unfold. The crowd-pleasing show, the side attractions, and how news reports steer our focus. Section 5 covers the immediate buzz, observation spots, media frenzy, and societal diversions. October's heavens are getting packed. Comet C/2025 R2 nears its nearest point to our world, hitting maximum around October 20th. Yet it's got company. Comet C/2025 A6, dubbed Lemon, is also gaining luminosity and appearing in northern skies at the same period. Twin comets, both catchable by hobbyist stargazers, both at perihelion mere days apart. It's a dazzling display. Such events are uncommon. They're the sort that draw eyes skyward. Add in the Orionid meteor display. The Orionids climax annually near October 20th to 21st, as Earth plows through remnants left by Comet Halley. That's right, the legendary Halley, returning every 76 years. Even at vast distances, its residue persists. A flow of icy grit and shards strung along its path. Each October, our world slices through it, with bits colliding into the air at 70 kilometers per second. They incinerate, streaking as luminous trails, meteors. The Orionids usually yield 10 to 20 per hour at zenith, occasionally higher. No grand tempest, but dependably consistent. Thus, come the evening of October 20th, 2025, expect dual comets gracing the view alongside a meteor peak. The night sky turns lively. Coverage in the press ramps up. Skywatching fans will swarm online with snapshots. Broadcasters will spotlight the stellar extravaganza. Prime opportunity for drawing in the public, yet also ideal for pulling focus away. As folks gaze at the Orionids, while lens wielders snap the paired comets, and front-page tales gush over the universe's splendor and awe. Scant attention goes to the tougher inquiries. Precisely how near is R2 getting? What's the error range? Any signs of splintering? Are we monitoring the scraps? What if surprises hit? The Washington Post highlighted the double comet phenomenon, pointing out that R2 and Lemon could be spotted via binoculars or modest scopes. They stressed the unusual nature, the allure, the thrill of dual sightings. Proximity took a back seat. No word on the minimum orbital distance. Fragmentation dangers went unmentioned. That's no knock. It's simply how outreach in science works for the masses. Wonder draws crowds. Hazard breakdowns don't. Then there's 3E Atlas, the star-hopping intruder, still hogging the spotlight despite its $1.8 Australian flyby. A harmless buffer by all standards. Outlets adore 3E Atlas for its enigma. It hailed from beyond our stars. It's reddish, or perhaps greenish, based on the data you credit. It shifts hues, or appears to, which is odd. Typical space rocks don't pull that off. It has ignited theories about artificial or speculation abounds regarding its beginnings, from extraterrestrial spacecraft to signals embedded in its path. Such ideas seem improbable, yet they captivate. They're engaging enough to spark clicks and shares online. In contrast, R2, the nearer interloper with its erratic path and episodes of sudden activity, receives far less attention. It lacks that otherworldly allure. As a likely product of the Oort cloud, it's firmly rooted in our solar system. No interstellar drama here. Just your typical comet, or so it appears. But that's misleading. This is a comet that evaded detection until it was practically upon us. It lurked in the sun's blinding light, revealing itself only post-perihelion. This comet could break apart at any moment, and it might still do so. Its minimum orbit intersection distance stands at 7 million kilometers, an uncomfortably narrow margin. Public interest hinges on the unfamiliar. Oumuamua was unprecedented. R2? Routine. Thus, Oumuamua dominates the news cycles, while R2 fades into obscurity. Yet obscurity can conceal real threats. Overlooked details often hold the key insights. We must proceed with caution in our assessments. Comets defy consistency. They flare up without pattern and dim just as erratically. They shatter abruptly, catching everyone off guard. Forecasts rely on historical patterns, but each comet charts its own course. R2 could surge to magnitude 4, turning into a visible wonder for the unaided eye. Or it might drop to magnitude 8, vanishing from sight. It could splinter, scattering debris everywhere. Or perhaps it simply drifts away uneventfully, retreating to the solar system's fringes and slipping from memory within a year. Uncertainty reigns. What remains certain is that this isn't a collision warning. The latest orbital calculations indicate R2 will pass Earth at 39 million kilometers, too distant for impact, but near enough for secondary concerns. Near enough for potential debris encounters. Near enough to boost meteor activity. Near enough that unforeseen fragmentation could send fragments veering toward earthbound paths. That's the essence of space hazards, not black and white outcomes, but a web of probabilities, unknowns, and if-then scenarios. Our monitoring infrastructure, the array of observatories and scanning programs we depend on for alerts, isn't equipped for such complexities. It's built for tracking steady objects on fixed trajectories. Unforeseen twists, like an object concealed by solar glare, a rapid brightening, or unexpected shedding, overwhelm the setup, leaving us scrambling to adapt. Now, let's delve further. We'll examine historical close calls, asteroids that zipped by Earth with scant prior notice, and the overlooked lapses in our surveillance that occur more frequently than most realize. Section 6. Real-world examples. Asteroids spotted mere moments before or after their encounters. Take early 2025, when the asteroid 2025 TF skimmed within roughly 400 kilometers of Earth's surface. Just 400 kilometers, closer than the International Space Station orbits. Closer than the bulk of our satellites. Deeper into space than numerous orbital installations. And it blindsided us until the last second. 2025 TF is modest in scale, likely spanning only a handful of meters. At that dimension, an atmospheric entry would have incinerated it harmlessly, producing a dazzling streak, but no surface harm. The 2013 Chelyabinsk event involved a 17 to 20-meter body that detonated overhead with energy equivalent to hundreds of kilotons of TNT. It demolished windows, harmed over 1,000 individuals, yet carved no impact scar. 2025 TF was tinier. It would have lit up the sky, end of story. But the issue isn't scale. It's the delay in spotting it. We remained oblivious until it was virtually overhead. The flyby occurred above Antarctica, Earth's most isolated expanse, monitored by hardly anyone. A minor shift in timing or path could have routed it over denser populations, and we'd have been caught completely unprepared. This isn't a one-off incident. Lately, multiple diminutive asteroids have surfaced in our catalogs mere days, hours, or minutes shy of their nearest pass. Others turned up post-flyby. They streaked past undetected by our instruments, only betraying their presence as they departed. Such oversights stem from inherent constraints in our observation grid. Scopes operate with brightness cutoffs. Tiny rocks stay dim. Solar direction approaches render them undetectable. High-velocity arrivals traverse the sky too swiftly for routine scans. Dark, low-albedo surfaces barely scatter light, merging seamlessly with the void. This isn't abstract theory. It's a tangible breakdown we witness repeatedly. We overlook objects. We do so routinely, typically learning of the lapse only when a vigilant observer scans the precise sky sector at the opportune instant and detects motion. The fallout is graver than it seems. True, the majority of these petite asteroids disintegrate benignly on entry, but exceptions exist. And a compact chunk, striking a vital asset squarely, could unleash devastating effects. Even a few meters of stone slamming into a satellite hitting something at orbital speeds would obliterate it right away. Crashing into the International Space Station would prove deadly. Even a modest projectile striking an urban area could demolish structures and claim thousands of lives. Our atmosphere offers protection, yet it's far from flawless. Items exceeding roughly 20 meters in size can make it all the way down. Smaller ones might still trigger destructive aerial blasts. Beyond that lies the problem of scattered remnants. As an asteroid disintegrates high up, it disperses chunks across a vast expanse. While many bits are minor, others could be sizable enough to inflict harm. Should the split happen above a crowded zone, those bits turn into lethal missiles. The Chelyabinsk incident flung meteorites across hundreds of square kilometers. Folks gathered them up as mementos. However, had the body been bigger or the fragmentation lower down, those pieces would have posed far greater threats. Now amplify this scenario. Picture not just one tiny asteroid, but a swarm of debris from a splitting comet. Rather than a handful of meters of stone, envision countless fragments, from fine particles to massive rocks, strewn along the path. Instead of one focused strike, think of a scattered peril, a probabilistic danger where individual hits seem improbable. Yet the overall odds remain significant. That's the nature of comet breakups. They don't deliver a lone projectile. They unleash a barrage. R2 boasts an amoid of 7 million kilometers, marking the distance between Earth's path and the comets. If fragmentation occurs and segments fan out along the trajectory, certain ones could inch nearer. Not to collision course, not to direct contact, but nearer still. Near enough to elevate the odds from trivial to modest yet real. And that modest yet real is precisely what keeps hazard experts on edge. This draws from cases like 2025 TF and similar threats. Delays in spotting them are a harsh reality. We miss plenty. We overlook most if they're tiny, swift, or approaching from odd angles. The space rocks we detect are those following the script, arriving via expected routes, from anticipated spots, at foreseen moments. The rule breakers, though, they're the terrors, precisely because they slip past us. Moving on, let's explore why comets can threaten without ever striking. How their rubble and particle paths generate ongoing risks long after the main body has passed by. Part 7. Comet splitting and dust trail perils. Plausible hypothetical cases. A comet might dodge us, but its leftovers can still sting. Allow me to break down the mechanics. Comets aren't dense boulders. They're flimsy collections of frozen water, grit, stone, and carbon-based materials, barely stuck together by faint pull and clingy surfaces. They're delicate. Nearing the sun subjects them to heat-induced fractures. Gas release builds force that rends them. Gravitational tugs from nearby giants. Should they venture too close, rip them asunder. At times, they crack subtly, dropping minor bits. Other times, they erupt dramatically, shattering into scores of shards. Take Comet Shoemaker-Levy 9 as the classic case. In 1992, it swung perilously near Jupiter, getting shredded by its gravitational grip. Over 20 fragments emerged, fanning across the orbital arc. 2 years on, they plunged into Jupiter sequentially, sparking colossal blasts observable from our planet. Every collision unleashed power matching millions of atomic warheads. The blemishes on Jupiter's clouds lingered for months. It was breathtaking. It also highlighted comet vulnerability and the menace of their splinters. Consider another instance, Comet 73P/Vassman-Vakman. This one split repeatedly. In 1995, it divided into multiple sections. By 2006, it crumbled once more, this round yielding dozens of tinier bits. Skywatchers witnessed the live unraveling, with each offshoot gaining its own fuzzy envelope and streamer. The pieces kept drifting apart, tracing subtly varied courses. Gradually, they crafted a rubble flow, a current of frost and powder tracing the prior route. Our world has crossed segments of that flow. It sparked a short spike in shooting stars. No apocalypse, but evident. Now extend this to R2. The comet's already flared at least once, hinting at inner turmoil. Should it shatter, the segments will part ways. The spread speed hinges on differing speeds, which tie to the breakup's force. A mild division yields gradual drift. A fierce burst drives rapid scatter. Regardless, fragments expand over time, along with the particles they kick up. Particles represent the true menace. Each comet constantly ejects grit as its ices vaporize. These specks are minuscule, mere microns to millimeters across, yet they zip along at dozens of kilometers per second. At such velocities, a mere speck packs tremendous impact force. Should a particle smack into a probe, it could breach the casing. If it strikes a sate, micrometeoroids pose a real threat in space, potentially harming solar arrays, instruments, or telecom gear. Striking an astronaut during an EVA could prove deadly. Take the ISS, for instance. It's equipped with protective barriers against these tiny projectiles. These defenses consist of several layers that aim to disintegrate approaching bits before they breach the exterior. Yet, they're far from infallible. Bigger chunks, or those coming in at odd trajectories, can still punch through. The station has endured numerous impacts over the years. While most result in superficial harm, a few have necessitated fixes. When a comet breaks apart, generating a thick trail of debris, the danger ramps up considerably. Think about the orbital setup next. Comet R2's closest approach is 7 million kilometers from Earth's path. That's the shortest separation between their trajectories. Should the comet shatter and its pieces disperse along its route, certain fragments could veer nearer to our planet's orbit. Not fully intersecting, not down to nothing, but nearer nonetheless. And if our world slices through that rubble at an inopportune moment, we could face an elevated barrage of particles. That might translate to a more intense meteor display. It could jeopardize orbiting satellites. It could lead to collisions with probes in flight. The odds of any single speck nailing a precise objective remain slim. After all, the void is vast. Assets are tiny. Still, the overall likelihood that at least one hit occurs somewhere rises. We're packing the skies these days with countless satellites, orbital outposts, and rough-hewn vehicles. Everyone counts as a possible victim. Don't overlook the interplay with our atmosphere, either. Should Earth plow into a heavy dust cloud, even from minuscule grains, the combined impact might show up visibly. Glow from upper air layers could intensify. Bolide occurrences might surge, those dazzling fireballs that burst high up. Hobbyists with telescopes would spot it. Dedicated meteor tracking setups would capture the oddity. Nothing apocalyptic, but definitely out of the ordinary. And oddities like that often set off warnings. The true worry isn't the visible grit. It's the unseen boulders. Picture a rock-sized fragment, say 1 or 2 meters wide, hurtling at 30 kilometers per second. It'd stay hidden until impact was imminent. Ground-based telescopes might detect it, but only by sheer luck, scanning the exact sky sector at the perfect instant. Approaching from the sun's direction? Undetectable. Featuring a low albedo or dark composition. Virtually impossible to pick out. slamming into the air over a crowded region? You'd get a Chelyabinsk-level blast, or bigger. Gauging the odds is tricky. We can't confirm if R2 has splintered yet. We don't know if it will. Nor do we grasp the potential number of shards, their dispersal patterns, size ranges, speeds, or paths. All that's certain is the main comet's trajectory and that 7-million km buffer from Earth's route. Given those limits, the chance of a piece striking our planet seems minimal. But minimal isn't nil. And with stakes involving human lives and vital systems, minimal might not cut it. Visual aids clarify this. Envision the comet's path as a strand woven through the cosmos. Now picture it unraveling, branching into scores or hundreds of finer strands, each veering just a bit. Some cling to the core route. Others wander off. Over time, this swarm forms a hazy band hugging the original orbit. Earth's loop is a separate strand, slicing across that band obliquely. Typically, we glide through clear expanses, but now and then we intersect the band. And that's when the debris cascades earthward. This isn't baseless conjecture. Annual meteor showers embody precisely this, trails of comet remnants. The Perseids, Leonids, Orionids, they're all such legacies. Yearly, our planet threads these trails, yielding shooting stars. Mostly benign, sometimes dazzling, seldom hazardous. Back in 1833, the Leonids unleashed a frenzy of tens of thousands of streaks hourly. Observers likened the heavens to a blaze. In our era, amid the satellite web, such an onslaught would wreak havoc. R2 isn't forecast to spark a storm like that. Its cast-offs, assuming any, are likely too scattered. But certainty eludes us. We'll only learn upon observation. And by then, response options might boil down to mere spectatorship. Up next, a broader inquiry. Are unexpected guests flooding in? Or is this merely a detection quirk? Is the solar system dishing out more intruders? Or are we simply getting better at spotting them? Part 8. Spotting Trends. Are surprise arrivals on the rise? Allow me to enumerate. Oumuamua showed up in October 2017, the inaugural verified interstellar interloper zipping our system. It was bizarre, cigar-shaped, spinning erratically, speeding up in defiance of standard vapor ejection physics. It departed before we could fully probe it. Examine it carefully. Next arrived Borisov back in August 2019, marking the second visitor from beyond our solar system. Unlike the first, this was unmistakably a comet, complete with a fuzzy coma, a trailing tail, and makeup matching the kind of junk we'd anticipate from a distant star's leftovers. Fast forward to 2025, and here's 3I/Atlas, yet another interstellar wanderer. Experts debate whether it's an asteroid or a comet core. Opinions vary. It shifts hues dramatically. Truly bizarre. Meanwhile, as everyone fixates on 3I/Atlas, R2 slips through quietly from right within our solar neighborhood, slipping past notice until well after its closest solar approach. That's 4 such intruders over just 8 years. Oumuamua, Borisov, 3I/Atlas, R2. Each boasts distinct backgrounds, varied makeup, unique spotting scenarios, yet all caught us off guard. They showed up with minimal warning, or none at all. Could this signal a trend? A spike in activity? Or simply the result of us at last tuning in properly? Experts float 3 possible explanations. Start with the idea of detection skew. Our tools have sharpened considerably. We've got superior scopes, broader sky scans, expanded citizen science via pro-level feeds for backyard stargazers. We're scrutinizing more intently, thus unearthing more finds. Setups like Pan-STARRS and the forthcoming Vera-C, Rubin Observatory specialize in spotting fleeting phenomena, zippy movers, anything that shifts. As these networks ramp up and refine, hit rates climb. This doesn't imply a flood of new arrivals. It suggests we're merely uncovering the steady stream that's been cruising by forever. Option 2. A genuine uptick in orbital churn. Or perhaps some force is jostling the Oort cloud. A star that swung by ages ago might have triggered an inbound comet swarm, with the vanguard only now reaching us. Our solar system could be traversing a denser patch of interstellar clutter right now. Or consider galactic pulls, the Milky Way's architecture gently prodding extra comets sunward. Far from outlandish, the Oort cloud spans vast expanses, harboring trillions of icy bodies. Even a minor nudge might dispatch thousands earthward across millennia. To us, bound by fleeting lifespans, it'd appear as an abrupt wave. The third take, mere chance clustering. Statistical fluke, nothing more. Chance events bunch up unpredictably. Toss a coin 100 times, and you'll spot runs of heads or tails. No foul play, just variability in play. These 4 surprise guests in 8 years could be mere static, a random blip without grand implications. The next 8 might bring 0 or a dozen. Lacking extra intel, it's tough to separate true patterns from background chatter. Supporting clues exist for all 3. Detection skew packs punch. The tally of tracked near-Earth asteroids has skyrocketed in the last 20 years, not from a sudden population boom, but from methodical hunts. Comets likely follow suit. Swan has unearthed hordes of them, especially sundivers, by catching what traditional optics miss. As our monitoring web grows, the inventory swells accordingly. Yet bias alone doesn't cover it all. Oumuamua was downright oddball. Its cigar-like form, unexplained thrust sands outgassing, absence of any noticeable haze, all puzzled the pros. A few theorized it as planetary rubble shredded by alien tides. Others floated frozen hydrogen bergs, nitrogen chunks, or icy gas remnants. Ideas escalated to the wild side since basics fell short. Then it vanished, squelching deeper probes. 3I/Atlas quirks out similarly. It flipped from reddish to greenish tones, or so some data suggests, if you buy those readings. Rocks from space rarely pull that stunt. Tint reflects makeup, so a shift hints at uneven exteriors. Rotation might expose varied facets catching light differently. Or subtle venting could tweak the glow, masking as a faint envelope. Or who knows, something wilder. Proximity's lacking to zoom in and settle it. Are 2 slots into the mix differently. Homegrown. Oort cloud origins probable, yet it lurked in solar blaze until post-perihelion reveal, underscoring our blind spots even nearby. If R2 evaded us, imagine the rest. Countless long-orbit comets zip innerward yearly, invisible? Unknown. We snag only the brighteners, the lingerers above our sensitivity bars. Others fade into oblivion. Pattern or not? Possibly. The upbeat view. Our gaze sharpens, revealing a cosmos buzzing with pop-ins, rubble streams, surprise drops. The downbeat. Influxes are ramping, and we're ill-equipped. Truth likely blends both. We're detecting more of these cosmic visitors these days, partly because we're scrutinizing the skies more intently. Yet, we're also realizing that the usual flow of interstellar traffic in our solar system runs at a brisker pace than previously estimated. Far from being a serene backwater, our cosmic locale buzzes like a bustling thoroughfare, and only recently have we started setting up the surveillance to monitor it properly. Moving forward, let's examine the organizations overseeing this influx, along with the data streams, the choke points, and the quiet periods that fuel doubts. Section on organizations, quietude, and the pathway from detection to widespread awareness. I'll guide you through the journey of how a find turns into common knowledge. Whether a seasoned expert or a dedicated hobbyist, someone notices an oddity, a drifting form, a sudden glow, a fleeting phenomenon. They log the coordinates, the timestamp, the brightness level. They verify if it's previously cataloged. Should it prove novel, they submit the details. To whom? The Minor Planet Center, MPC, run by the International Astronomical Union. This hub serves as the central depot for sightings of asteroids, comets, and similar minor entities. It gathers inputs from spotters across the globe, cross-checks them, and releases alerts once novelty is established. However, validation demands patience. One sighting alone won't suffice. Confirmation requires several independent views to validate the target's existence, eliminate equipment glitches, and derive an initial path, which involves holding out for additional watchers to train their scopes on that sky region and back up the initial report. Should the target be dim, hovering at the edge of visibility, or zipping along swiftly, the process might drag on for days or even weeks. Upon validation, the MPC grants a temporary label and distributes a digital bulletin. The information goes live for all to access, though it's unprocessed: trajectory parameters, location data, brightness approximations. This isn't crafted for broad appeal, no media blast or front-page story. It's a specialized report aimed at fellow stargazers. Everyday folks skip NPC bulletins. They turn to journalistic pieces instead. And those pieces arrive belatedly, if they show up at all. In the interim, other groups polish the trajectory details. The Jet Propulsion Laboratory, JPL, operates Horizons, a tool for computing accurate paths of solar system denizens. With incoming data piling up, the trajectory model sharpens, error margins narrow, and forecasts gain solidity. If the item seems risky, say, its path grazes Earth's vicinity, JPL marks it accordingly. The Center for Near-Earth Object Studies, CNEOS, then assesses the danger level. Should the peril warrant it, NASA puts out an official notice. If it's minor, they may stay mum. For R2, events unfolded in this manner. Vladimir Bezugi, a keen amateur stargazer, picked up the anomaly in swan imagery on September 11, 2025. He flagged it. Fellow observers validated it through direct viewing. The MPC released a notice, labeling it C/2025 R2. JPL crunched the orbital numbers. CNEOS reviewed them. The verdict, no danger. Its nearest pass would clock in at 0.26 astronomical units, safely distant. No media alert, no alert to the masses, merely a routine entry tucked away in archives. That's the origin of the hush. Not from any cover-up or shadowy plot, but from a framework built for hazard control rather than audience outreach. Non-threatening items don't snag spotlights. Without that buzz, they slip past most radars. R2 popped up in select astro publications and space-focused sites. It even featured as the astronomy picture of the day on September 18th. Yet it never lit up social feeds or seized the headlines. Just one more comet amid the annual haul of scores. Compare that to 3I/Atlas, an interstellar oddball with erratic hues and bizarre speed shifts. That screams for coverage. Such tales snag attention from major outlets, ripple through online shares, and spark endless debates in forums. It doesn't count that 3I/Atlas is benign, with a minimum distance of 1.8 astronomical units and 0 peril. What counts is its intrigue, and intrigue drives clicks. This breeds empty spaces when official bodies withhold clear, user-friendly briefings. When the info progression crawls along in jargon-heavy terms, when the span from spotting to general notice balloons into weeks or months, guesses rush in to occupy the void. Online communities spot these lulls. They probe, why the scan updates? Why so little buzz? Is info being suppressed? Lacking prompt official replies, alternative narratives sprout, speculations, plots, whispers. The case of Vladimir Bezugi unearthing R2 offers key lessons. He's no career astronomer, unaffiliated with any space outfit. He's a hobbyist skilled at sifting swan feeds. That he beat the pros to the punch isn't their shortcoming. It underscores the gaps in our spotting web, the value of unconventional routes, and how pivotal finds can hail from unlikely sources. Still, it prompts inquiries. If an amateur can spot a comet, what other discoveries might professional surveys have overlooked? How many more objects zip through the inner solar system without detection, simply because they're in the inconvenient spot at an inopportune moment? Or because the telescopes are pointed in different directions? Or thanks to overly bright skies, lousy weather, or downtime for equipment repairs? The truth is, we have no clue. It's impossible to know for sure. That's the core issue here. The process for handling data is deliberately methodical. Double-checking helps avoid bogus alerts. Being prudent stops widespread hysteria. Yet that same prudence opens up blind spots, and those blind spots breed uncertainty. When folks lose faith in official bodies to deliver straight facts, they turn to other outlets for answers. Unfortunately, those outlets aren't always trustworthy. Moving on, we'll now sort through the outlandish notions, the conspiracy theories, and the offbeat speculations. We'll sift out what's potentially viable from the rest. Part 10. Wildcards and Conspiracies. To be upfront, some will insist that R2 isn't a natural formation. They'll claim it's a scout, a vessel, a manufactured gadget dispatched by an entity to monitor humanity. They'll point out the path seems too neat, the schedule too spot-on, the flare-up too deliberate. They'll accuse NASA of withholding key details, burying photos, and locking away genuine findings under secrecy. They'll view it as a signal, an alert, an experiment, and they'll be convinced. So, Let's evaluate these ideas methodically. We'll tackle each assertion individually and determine if any merits serious thought. First assertion, R2 is man-made or alien tech. Could that happen? Theoretically, sure. An advanced society might construct a probe disguised as a comet. They could encase it in frost to generate a hazy envelope under solar heat. They could set it to erupt predictably. They could plot its course for a near-Earth flyby. It's feasible, but far from straightforward, and it would leave telltale signs. If R2 were engineered, we'd anticipate oddities. Spectral analysis might reveal bizarre makeup, rare elements, or compounds alien to typical cometary stuff. The core might display patterns, symmetrical forms, or uniform features absent in raw space rocks. The path might exhibit precise tweaks, subtle corrections unexplained by mere gas ejections, plus radio waves, heat glows, or other hints of powered operations. None of that's appeared. The light profile matches a standard comet. The envelope aligns with vaporizing frost. The route adheres to gravity's pull. No transmissions detected. Occam's razor reminds us. The plainest answer tends to be right. R2 resembles a comet because that's what it is. Positing engineered routes demands extra layers, and proven forces, intricate designs, mysterious players with hidden agendas, and unexplained tech. It's conceivable, but superfluous. Science sticks to essentials, avoiding needless hypotheses. Second assertion, visuals are being censored. Do we get the full picture? Likely not entirely. Top-tier facilities don't release every snapshot. They refine the raw feeds, adjust for accuracy, weed out glitches, and pick prime shots. Certain info stays exclusive to the proposing scientists. Some footage is subpar, unworthy of sharing. But outright hiding suggests motive, a plot to conceal truths. That would demand tight-knit collaboration, which is tough to pull off. Facilities span the globe, running solo. Hobbyists wield their own gear. If anything striking showed up, it'd leak online fast. The absence of stunning shots probably means none exist rather than a cover-up. Third assertion, the path is being guided. Might some outside influence be directing R2? If aliens are involved, that's back to the first point. If natural, absolutely. Gas releases produce extra pulls beyond gravity. Comets aren't straight shooters. They nudge their own ways via expelled vapors. R2's flares indicate such venting, which warps its line. JPL's simulations factor in those extras. They adjust for the venting effects. Forecasts aren't flawless, but they're solid. Active steering would show model-defying quirks unaccounted for by gas alone. Nothing like that. Fourth one, it's benign yet portentous. Certain voices contend that even if R2 poses no threat, even if it skips us entirely, its showing up carries weight. A symbol, a portent, a cosmic coincidence. This isn't science. It's more metaphysical or mystical. Research can detail the path, the makeup, impact odds. But interpreting cosmic intent? That's beyond testable evidence. If a comet's timing feels profound to you, that's fine. Just don't mix subjective insight with tangible dangers. That said, are there ideas needing deeper scrutiny? Indeed. For starters, the risk of breaking apart and scattering fragments warrants real attention. It's not some shadowy plot. It's straight-up physics. When a comet like that breaks into two main chunks, any smaller bits that veer off from the main path could pose risks. We're talking not so much a collision danger, but more like orbiting junk, a stream of tiny meteoroids, or threats to satellites, stuff we need to keep tabs on and plan for. Sure, it's hypothetical, but it's rooted in solid knowledge of how comets act. Here's how the assessment breaks down. Man-made cause? No proof, so unlikely. Hiding the images? Doubtful, considering observations came from all over. Altering the path? Nothing points to it except normal gas venting. Hidden symbolism? That's not science. As for breakup debris? Totally possible, and definitely merits watching. Daydreaming about it is enjoyable. It's just in our DNA to spot connections, attribute intent, and weave tales into the unknowns. Yet we must be willing to pit those ideas against real evidence. And if the facts don't back the narrative, we've got to muster the resolve to drop it and press forward. All right, time to change direction. Let's dive into some fresh science news. Kicking off with brain research, since the mind itself is a kind of sensor array with its own weaknesses. Section 11, Brain Science. UCSF discovers molecule that curbs neural decline. Back in August 2025, scientists from the University of California, San Francisco, released results about a protein that seems to influence how the brain ages. Tests on older mice pinpointed this protein, which acts like a brake on the brain's adaptability. Once the team inhibited it, those senior mice displayed better recall and quicker learning. Their nerve cells sparked more consistently. Connections between synapses grew stronger. In certain tests, their brains operated almost like those of juveniles. The setup was simple. Grab aging rodents, spot the protein that builds up over time, shut it down with meds or gene tweaks, then check for behavioral gains. Outcomes looked good. Treated elder mice aced memory challenges. They zipped through labyrinths with ease. They identified items more accurately. The changes were clear-cut, reproducible, and backed by strong stats. Still, this is all rodent-based. Rodents aren't people. Their brains are less intricate, tinier, wired in unique ways. Successes in mice don't guarantee human wins. Neuroscience's track record is full of fixes that healed animals but bombed in people trials. We've solved Alzheimer's in mice countless times. Folks are still hanging on for real progress, so we tread carefully. These discoveries thrill, yet they're early stage. If they carry over, the ripple effects could be huge. Losing mental sharpness tops the dread list for getting older. Forgetting things, struggling to pick up new skills, sluggish thinking. These erode freedom and self. Halting or undoing that slide with one protein target. That could reshape lives and whole communities facing graying demographics. Dementia drains trillions worldwide in economic hits. Even pushing back its start by a handful of years would free up fortunes and ease immense pain. Complications arise, though. Proteins don't operate solo. They're woven into webs, chains, regulatory cycles. Tampering with one could trigger ripple issues, throw off balance elsewhere. No glaring side effects popped up in the study's old mice, but follow-up was brief. Long-haul impacts remain a mystery, and people are trickier. We endure more years. We pile on extra wear. We juggle multiple health woes. A neat fix in mice could clash wildly with our physiology. Consider this analogy. The mind functions as a scanner. It sweeps surroundings, handles inputs, stores experiences, forecasts outcomes. At peak, it snags nuances. It adjusts. It absorbs. As years pile on, acuity fades. Inputs dim. Interference builds. It's tougher to discern shapes. That UCSF-spotted protein plays into this wear down. Neutralizing it helped regain some of the brain's fresh vigor. Now, pivot to our space-watching gear. Scopes sweep the heavens, sift data, log finds, forecast paths. Operating smoothly, they nab dim comets. They follow rocks. They flag dangers. But gear wears too. Tools wear out. Detectors wander, tuning slips, info flows clog with junk, and gradually we overlook signals we'd once grabbed. The comparison isn't exact, but it's revealing. Weather mines, or scopes, both are crafted to pick out signals amid chaos. Both erode with time. Both might rebound, somewhat, via tweaks. For brains, perhaps a protein inhibitor. For scopes, maybe retuning, new parts, better software. The core idea holds. Staying alert demands upkeep. The UCSF work underscores how unseen forces shape our perceptions and our oversights. Occasionally, the issue stems from biology, like a protein building up over time. Other times, it's tech-related, such as a sensor slipping out of calibration. Or it could be organizational, perhaps a polling timeline that misses key details. The fix remains consistent regardless. Pinpoint the process, grasp its operations, and step in to fix the breakdown. Now, let's examine yet another big news item from neuroscience. This one's focused on Alzheimer's, since the cycle of flashy announcements and sobering truths merits a closer look. Section 12. The Alzheimer's breakthrough buzz in October 2025. That month unleashed a fresh round of buzzworthy stories. Alzheimer's cured in mice, blared the reports. Coverage brimmed with excitement, while online shares radiated optimism. Truth be told, things were far more nuanced. Scientists experimented with a fresh approach, maybe boosting blood flow, or sweeping away amyloid buildup, or tweaking protein levels. Specifics shifted across reports, yet the core idea held steady. Older mice plagued by memory woes bounced back post-treatment. Plaques vanished from their brains. Recall abilities sharpened. Certain disease markers even flipped back. Not a novel occurrence, either. Over the last 20 years, Alzheimer's work has churned out scores of hopeful rodent experiments. Shots to dissolve amyloid, meds to shrink tau tangles, genetic fixes to revive neural connections. Rodents respond brilliantly. People? Mostly these flop. The leap from lab to clinic is vast. Rodent versions of Alzheimer's fail to mirror the full human ordeal. Mice don't stick around long enough for the disease's complete progression. Their neural wiring is less intricate. Immunity differs. Metabolism races ahead. Something effective in a brief 6-month mouse trial could crumble in a decade-long human one. Group sizes count heavily. Rodent tests might involve just a handful of subjects. Human studies demand thousands. Time frames are crucial too. Mice wrap up in months. People endure years. Hidden risks play a role. A substance harmless in mice could poison humans. Results vary widely. Boosting rodent memory by 20% might translate to a mere 5% in us, and that slim gain may not shift daily life meaningfully. Summaries in outlets like Newsweek, much like other mainstream science pieces, spotlight the upbeat angles, turnarounds, game changers, optimism, since drama drives clicks. Yet the raw studies themselves tread lightly. Phrases like initial, constrained, needs more probing dominate. They spotlight the hurdles in adapting findings. Victory? Hardly. Just steps forward. The rub lies here. Intricate findings morph into explosive news bites. Subtleties vanish. Doubts get scrubbed. The divide between true discoveries and public perceptions widens. Then, when human tests tank and trials flop, folks feel duped. A remedy was dangled. Instead, letdown strikes again. Confidence crumbles. This cycle plagues Alzheimer's alone. It's rife wherever the pressure's intense and the work's thorny. Oncology, environmental modeling, pathogen battles, and indeed, stargazing too. Spot a fresh comet? Press hypes dazzling shows, rare spectacles, easy backyard views. Often, it's murkier, shakier, tied to unpredictable factors. Comets dim out. They break apart. They underwhelm. Crowds awaiting fireworks end up deflated. The takeaway? Healthy doubt, minus the bitterness. Doubt. Spot a story touting a major advance. Dive into the original papers. Scrutinize participant counts. Hunt for qualifiers. Probe what data they gathered versus what they concluded. Unpack the constraints. Forecast the follow-ups. Usually, it's further investigation called for. And that's okay. It's science's rhythm. Headlines, though, crave absolutes. Science thrives on odds. The tie-in to R2? Solid. The comet exists. Sightings hold up. Path projections check out. But forecasts on GLOW break up risks? Pure chances. Future unfolds unknown. We gauge potentials across likelihoods. The smart move. Lay out those odds plainly. No hype. No downplay. No sensational spin for traffic. Moving on to machine learning next. A realm where buzz clashes with facts, yet one reshaping how we spot space dangers too. Section 13. AI drops in October 2025, plus ethics debates. The month featured a slew of AI unveils. Fresh architectures, innovative utilities, expanded powers, plus open access drops expanding machine smarts edges. Core systems boasting sharper logic, superior context grasp, quicker outputs. Firms and academic teams rolled out platforms able to handle extended contexts. It enhances coherence in intricate reasoning processes, produces code with greater dependability, and interacts seamlessly across various modalities at once. The rate of advancement remains unyielding. Tasks that felt unattainable just 2 years back are commonplace now. What's standard today will likely become outdated within another 2 years. This speed-up is tangible, quantifiable, and displaying no indications of deceleration. Paralleling the technological strides and moral imperatives, efforts to synchronize AI evolution with societal principles have emerged at international conferences, supported by experts and regulators. While specifics differ, the central message endures. AI holds immense power. It's advancing rapidly, and we must ensure it reflects our genuine desires, not merely our superficial wishes, but the core principles that matter when outcomes turn serious. The issue extends beyond AI's capabilities to what it ought to achieve. And who holds the authority to determine that? These aren't mere theoretical debates. They're pressing, real-world matters. With AI growing ever more proficient, independent, and woven into vital systems, the risks escalate. An error in health assessments could prove fatal. A flaw in transportation management might lead to collisions. A blunder in space monitoring could blind us to approaching dangers. In the field of astronomy, AI is already integral to data processing workflows. This isn't conjecture. It's established procedure. Automated systems for spotting irregularities examine sky images for fleeting occurrences. AI models categorize celestial bodies, differentiating between asteroids and stars, comets and galaxies, supernovae and fluctuating stars. These identifications occur in fractions of seconds. A person might require minutes or even hours for identical tasks. Software optimizes paths, using collections of location data to compute paths. It forecasts upcoming locations, gauges error margins, highlights items with trajectories nearing our planet. It identifies possible dangers, items that could threaten impacts, potentially warranting additional scrutiny or inclusion on monitoring rosters. The sheer amount of data exceeds what people can handle by hand. Contemporary broad-scale sky surveys produce terabytes of information nightly. Every photo holds millions of entities. Each entity demands measurement, recording, and comparison against prior archives. Ephemeral phenomena, those that emerge, vanish, or alter in luminosity, require detection and marking. The Vera Rubin Observatory, upon full operation, will capture the whole observable universe every few nights. It will spot billions of entities. Among them, tens of thousands will be in motion, evolving, or temporary. No group of humans could manage that influx. AI is essential to sort through it, to uncover the key indicators amid the clutter. Absent AI, contemporary stargazing would be swamped by its triumphs, buried under the torrent of data streaming from observatories each evening. Yet AI isn't flawless. It errs. It highlights spurious alerts, items resembling threats that aren't. A cosmic ray strikes the sensor, creating a vivid trail. The AI interprets it as a swift celestial body. It marks it as a prospective asteroid. Subsequent checks reveal emptiness. The entity never existed. It was a flaw, a malfunction, an illusion, or the AI mislabels it. A remote supernova intensifies slowly. Its brightness profile resembles that of a pulsating star. The AI places it incorrectly. Days elapse before someone spots the mistake and corrects it. By that point, the prime viewing period has ended. Vital information has slipped away. It overlooks authentic indicators, particularly if they're atypical or diverge from the learned patterns. AI frameworks draw from datasets. Present the model with countless asteroids, and it grasps their appearance. Provide thousands of comets, and it discerns their traits. But what occurs with an arrival that defies those samples? What if an entity exhibits characteristics beyond the AI's trained scope? The model could dismiss it as interference, a defect, or something dismissible, or misplace it, directing it erroneously. In any case, the crucial data vanishes, and it can exacerbate prejudices. If the dataset favors particular object types, the AI inherits that slant. Imagine the bulk of training from visual scans in specific sky regions. During set seasons and conditions, the AI absorbs those habits. It expects asteroids to exhibit particular luminosity levels, hues, and speeds. Then something outside that norm appears. Perhaps it's unusually dim, with reduced reflectivity. Perhaps its pace is quicker or lethargic. Perhaps it originates from an odd angle. The AI, shaped by the skewed data, fails to identify it. It discards it. It will detect what it was designed for and overlook the rest. There's also the deluge of interference. As artificial intelligence improves in spotting irregularities, it produces a flood of notifications. At first glance, this seems beneficial. Greater detection rates suggest improved oversight and reduced oversights on actual targets. However, the influx of notifications demands extensive verification checks. These checks require additional telescope usage, increased staff involvement, and heightened resource demands. Observatories come at a steep price. Access to a prominent one runs into thousands of dollars hourly. It's impossible to investigate every notification. Prioritization becomes essential. Astronomers must determine which phenomena merit the expenditure and which don't. When the rate of erroneous positives remains elevated, the entire setup becomes bogged down. Researchers end up expending their efforts pursuing illusions while overlooking genuine dangers. Striking a balance between detection accuracy and false alarm rejection proves challenging. Detection accuracy refers to catching authentic signals effectively. False alarm rejection means dismissing spurious ones reliably. Ideally, both metrics should excel. Yet, reality imposes compromises. Boosting detection accuracy captures more true positives, but also invites additional errors. Enhancing false alarm rejection filters out more errors, but risks bypassing legitimate finds. The optimal balance, nabbing the majority of actual hazards without excessive spurious triggers, is precarious and ever-changing. Factors like data reliability, environmental viewing factors, and target properties influence it. Ongoing adjustments, iterative responses, and persistent expert supervision are vital. Consider this imagined case. An AI system reviewing comet luminosity records highlights an odd surge in R2's brightness profile. The comet had been gradually intensifying since its initial spotting, aligning with rising solar exposure as it neared the sun. Then, on October 15th, the luminosity spikes abruptly, not dramatically, perhaps just half a magnitude, but the rise is steep and sudden, defying the smooth progression forecasted by simulations. It resembles an outburst, yet the schedule feels off. The sequence doesn't align with prior outbursts. Those had occurred around perihelion, during peak solar warmth. This instance arises weeks afterward, as the comet recedes from the sun. That's atypical. Could it be genuine? Or perhaps an equipment glitch? Possibly a misalignment in the telescope's tracking. Atmospheric shifts might have played a role. Calibration issues could explain it too. Alternatively, might it signal an unforeseen event? Like a physical alteration in the comet, ejecting debris, impacting a meteoroid, or a volatile pocket bursting forth in a sudden release. The AI lacks the insight to discern. It doesn't grasp underlying physics, nor does it possess detailed comet dynamics models. It simply measures the input against familiar templates. This template stands out as atypical. Thus, it marks the irregularity and routes it to a specialist. The astronomer gets the notification amid a barrage of others that day. She examines the records, notes the surge, and cross-references auxiliary tools. Has R2 been monitored by others lately? Do separate readings validate the luminosity shift? She queries the archives. No matches. The surge shows up solely in this one collection. That's concerning. Glitches typically confine themselves to isolated records. Authentic occurrences often manifest across various sources, barring fortuitous timing where just one scope caught it. She reviews the session notes. Any hiccups that evening? Troubles with the instrument, sensor, or skies? The entries note patchy clouds and fluctuating visibility, but nothing out of the ordinary. She inspects pre- and post-surge visuals. The comet appears routine. No clear morphological shifts, no fresh debris, no sustained glow afterward. The surge was fleeting, assuming it happened. Perhaps mere fluctuation or a valid but short-lived pulse, too brief for corroboration elsewhere. She weighs her options. The proof is inconclusive. The surge might hold truth, but likely stems from an error. Lacking validation or extra inputs, broadcasting a warning feels hasty. It would drain assets, prompt extra scans, rally fellow experts, and if it proves baseless, squander collective effort. She opts against alerting. The irregularity gets recorded as unverified, archived, and set aside. She advances to the subsequent notification. Operations persist, yet suppose it was authentic? Imagine the surge hinted at breakup, with fragments now veering from the main path. Under ambiguity and partial info, the expert's judgment could overlook a key development. Separation demands time. Initially, in mere hours or days, fragments hug the core, tough to distinguish even via sharp imaging. Once spaced enough for individual identification, they could have strayed sufficiently to present independent risks. Meanwhile, the AI that first noted the oddity faces dismissal, not due to oversight on her part. She adhered to guidelines. She assessed the indicators. She reached a sound conclusion. Still, conclusions drawn amid doubt occasionally falter. Gradually, Operators grow wary of the AI's signals because most of these signals turn out to be mistaken alerts. This phenomenon is known as alert fatigue, something extensively studied in areas like healthcare diagnostics, flight safety, nuclear facility management, and increasingly in astronomical observations. When warnings trigger excessively without leading to actual issues, individuals grow less reactive and urgent. They start ignoring them. They create shortcuts to sift through the clutter. Perhaps they'll only act on notifications scoring over 90% certainty. Or maybe they'll pursue leads only when several devices detect the identical item. Or they might downplay warnings from outdated scopes prone to alignment problems. Such shortcuts make sense. They conserve effort. They direct efforts toward the likeliest prospects. Yet occasionally, these filters block out the true alerts as well. The authentic danger, the one that truly counts, could rate just 85% on the scale. It might register on a single device simply because that's the only one pointed in the right direction at that moment. It could originate from an aging instrument that, for all its flaws, still spotted something legitimate. And so, when that notification pops up, it's brushed off as irrelevant clutter. The very mechanisms humans use to manage data overload end up obscuring real outliers. This underscores the hurdles in partnering humans with AI. Neither side is flawless. AI excels in speed, yet lacks depth. It crunches enormous datasets in mere moments. It spots trends that would take people hours to notice. It never wearies. It maintains unwavering attention. However, it misses nuance. It lacks gut feelings. It can't assess if an oddity aligns with physical principles. Humans, by contrast, operate more deliberately but with greater insight. They grasp the laws of nature. They rely on instincts. They evaluate cause and effect and feasibility. Still, they're constrained by focus, exhaustion, and mental shortcuts. They can only review a fraction of the information. They overlook events beyond their current scope. The optimal setup leverages their strengths together. AI manages the sheer scale, while humans provide discernment. The machine combs through all inputs, highlights deviations, and hands them off for review. People then scrutinize the potentials, layering in background knowledge and hunches to sort the valid from the spurious. But success demands confidence, fine-tuning, and iterative adjustments. Operators need to believe the AI isn't overlooking vital cues. The AI has to be adjusted to deliver useful pings without flooding the system. Plus, there should be ways for users to signal hits or misses, allowing the setup to evolve and refine itself. Above all, people must stay alert, avoiding overconfidence or the notion that AI covers every base. The instant they view AI as error-proof, a flawless sentinel that catches it all, the whole arrangement turns risky. Since AI isn't error-proof, it's a potent instrument, yet bounded, needing human supervision to operate effectively. The real peril isn't AI's shortcomings. It's excessive reliance on it, leading to lapsed vigilance. Once attention wanes, oversights pile up. Detection today transcends mere equipment. It's no longer solely about constructing larger observatories with superior optics and keener sensors. It involves code. It encompasses routines. It includes branching logic, machine learning models, and probability cutoffs. It's the guidelines we devise to separate meaningful data from static, the simulations we craft to forecast paths, the workflows we design to handle inputs. And everything stems from human input, shaped by human-curated datasets, applied in human-defined scenarios. The prejudices, omissions, and oversights, those are human imprints. They're decisions, intentional or not, woven into our creations. AI extends our vision, but it can't resolve the core dilemma. We're hunting for signatures in a cosmos indifferent to our success. The cosmos doesn't tailor itself to our methods. It doesn't simplify the hunt. Bodies approach from awkward directions at awkward moments, bearing awkward traits that defy our reference materials. They lurk amid solar interference. They show up amid cloudy skies. They break apart erratically. Our monitoring frameworks, whether operated by people or machines, must adjust to this unpredictability or falter. The task goes beyond crafting superior instruments. It's about fostering stronger synergy between those instruments and their operators. Moving forward, we'll draw on another brain science investigation. This one explores spatial recall and its waning in older age. serving as an analogy for how monitoring setups deteriorate progressively. Section 14. Metaphor of equipment and detector wear. Stanford's work on spatial memory and aging. On October 3, 2025, Stanford scientists released results detailing the erosion of spatial memory in maturing brains. They examined cells in the hippocampus, the cerebral area tasked with constructing mental layouts of surroundings. These aren't vague diagrams. They're brain-based depictions of tangible areas, forged from lived encounters and honed via practice. In juvenile creatures, these brain cells activate dependably whenever the organism reaches a particular spot. The activation sequence is exact, steady, and repeatable. Neuron A activates upon entering corner 1. Neuron B triggers in corner 2. This sequence forms a cognitive blueprint, a brain-based grid that enables the creature to pinpoint its position and plot routes to desired destinations. Yet in older specimens, the cells activate with reduced dependability. Neuron A could activate in corner 1, or perhaps corner 2, or remain silent entirely. The blueprint turns hazy. Spots merge indistinctly. The creature senses its general presence, but lacks sharp localization. Wayfinding grows challenging. The organism pauses uncertainly. It retraces steps. It veers off course. It attains the objective in the end, though the route proves roundabout, erratic, and riddled with missteps that a youthful counterpart would avoid. Researchers pinpointed the process driving this deterioration. Specific proteins build up over time, attaching to junction points and curbing adaptability. Junction adaptability refers to the capacity of neural links to intensify or diminish according to encounters. It underpins the mechanics of acquiring knowledge and retaining it. As adaptability wanes, cells forfeit their power to refine the blueprint, fix inaccuracies, or integrate fresh data. The outcome is a diminished depiction of surroundings. The blueprint persists, but it's obsolete, vague, and undependable. The creature continues to maneuver, yet with diminished precision. Errors multiply. Destinations take extended effort to locate. The downturn unfolds slowly, understated initially, yet quantifiable. Gradually, it intensifies. Flaws build up. The blueprint erodes. This discovery extends beyond brain science alone. It serves as an analogy for all sensing apparatuses humans have constructed. Astronomical scopes age through identical processes. Devices begin crisp, accurate, tuned to capture the weakest emissions, but gradually they falter. Lens positioning shifts. The reflectors channeling celestial light rest on frameworks that swell and shrink with heat variations. Across months and years, minute displacements pile up. Sharpness dulls. The view diffuses. Rays meant for one sensor point scatter over multiple. The spread profile, the formula outlining how a scope depicts a pinpoint emitter, expands. Clarity diminishes. Reflectors gather grime. Even in premier facilities, even in enclosed setups, fine particles deposit on lens areas. Grime disperses rays, cutting the flux to the sensor. More severely, certain scopes face outdoor conditions. Breezes haul debris. Heat swings spawn moisture buildup. Eventually, the reflector face corrodes. Metal layers deposited for bounce-back erode. Bounce efficiency falls from 98% to 95% to 90%. Each lost percent signifies reduced light particles gathered. Dimmer targets overlooked. In time, the reflector requires stripping and recoating, an operation spanning weeks and running into hundreds of thousands of dollars. Detectors accrue flaws. Pixel arrays, the chip arrays transforming light into charges, suffer harm from space radiation. Intense particles collide with the chip framework, displacing elements, generating faulty spots that output bogus readings. Inactive spots emerge, regions where light hits but yields no output. Interference motifs arise, pattern distortions needing removal in data handling. The sensor functions onward, but its response span narrows. Its responsiveness drops. Targets at the edge of capture, the faint ones yielding just a few particles per scan, sink beneath the interference level. They disappear. Alignment tuning loses accuracy. Each scope demands routine tuning to translate sensor readings into valid data. You aim at verified bright stars, gauge the output, and construct a response graph. But tuning strays. Sensor behavior alters. Light passage varies. Atmospheric conditions shift. Without regular retuning, readings turn suspect. A target deemed magnitude 6 could truly be 5, 8, or 6.2. That vagueness spreads. Intensity assessments grow dubious. Trajectory forecasts relying on intensity falter. Uncertainty margins widen. Views blur further. Capture limits elevate. Items once detectable with firm, assured readings now linger near the brink of reliability. Is that streak a comet or an artifact? A drifter or a radiation strike? Doubt escalates. Watchers grow wary. Extra scans demand attention, yet scope access is limited. If each borderline find needs validation, the workflow stalls. Backlogs swell. Targets shift away unverified. We lose them. Upkeep aids, yet reaches limits. Reflectors can receive polishing. Grime yields to gentle swabbing or blasts from pressurized gas. But polishing brings there's a risk involved. A mere scratch, a faint smudge, or leftover residue can exacerbate issues. Reapplying the aluminized coating revives the mirror's reflective properties, yet it demands dismantling the optic, transporting it to a specialized facility, enduring several weeks for the treatment, followed by reinstallation and precise realignment. In the interim, the observatory remains inactive. Data collection halts. The ongoing survey comes to a standstill. Celestial bodies that could have been spotted in that period slip through undetected. Detectors can be swapped out. Upgraded CCDs offer improved quantum efficiency, reduced noise levels, and broader dynamic range. Such options exist, though the swap proves costly. One unit alone might run into millions of dollars. Fitting it in calls for meticulous care. The device needs chilling to cryogenic levels to minimize heat-induced interference. Supporting chillers require ongoing upkeep. Issues arise, seals break, compressors malfunction, setups shut down, and even a fresh sensor can't overcome the wear in the broader optical pathway. Ultimately, the instrument's performance hinges on its most vulnerable part. Recalibration offers another avenue. Ideally, nightly adjustments occur via reference stars, verifying the baseline magnitude and assessing atmospheric absorption. Reality, however, brings obstacles like cloudy skies. Timetables delay. Software workflows rely on outdated calibration data. Subtle shifts evade notice until an audit reveals skewed readings. At that point, potentially weeks or months of observations could be tainted. Derived orbital paths propagate those inaccuracies. Targets get positioned wrongly. Forecasts prove unreliable. Yet upkeep demands substantial effort, schedules, funds, and skilled personnel. Allocations remain limited. Granting bodies favor launching fresh endeavors over sustaining legacy equipment. After launch and initial success, the buzz dissipates. Media coverage shifts elsewhere. Original architects step away into retirement. Constructors shift to novel ventures. The hosting organization inherits a deteriorating apparatus with dwindling support. Routine servicing gets pushed back. Enhancements are shelved. Where outpaces fixes, disorder prevails. Research from Stanford illustrates that even self-maintaining organic structures, which renew themselves nonstop, succumb to decline over time. Nerve cells falter despite the mind's prowess in forming fresh links, trimming idle pathways, and reshaping circuitries. The hippocampus stands as a rare cerebral zone generating new cells lifelong. Neuron formation persists well into seniority. Still, this renewal power falls short of offsetting built-up harm. Connections fade, proteins build up, cognitive layouts grow faulty. The slowdown proceeds more gradually thanks to self-repair, but decline remains unavoidable. Unlike these, our stargazing tools lack such resilience. They don't self-maintain or renew. Harm lingers until manual correction. Such fixes drag on, cost a fortune, and seldom fully restore. A polished surface today gathers grime anew by morning. A new sensor fitted now develops faulty spots within a year. A fresh alignment today veers off come next month. The erosion presses on unyieldingly. It accelerates beyond living systems due to absent inherent fixes. As tools deteriorate, discoveries evade us. R2 exemplifies detection oversights. The comet surfaced belatedly, obscured in a solar positional void amid daylight glare. Yet voids aren't solely spatial. They can stem from equipment flaws. A dim wanderer teetering on detectability might register clearly on a modern scope with a recently recoat surface and flawless array. The identical body, viewed seasons hence via the identical rig, now dust-laden and pixel-compromised, could vanish from view. The visitor stays constant. The viewer alters. Due to that decline, spotting fails. The very same entity, probed identically, yields varying outcomes based on apparatus condition. This isn't mere theory. It unfolds routinely. Patrol scopes log fewer finds in later phases than startups. Despite an unaltered cosmos, the drop ties to worn components, dulled lenses, and array breakdowns. Without adjustments, regular trials, fresh tunings, ongoing monitoring of capability, we overlook prior catches. Awareness escapes us since absences never register. They haunt as unseen specters, untraced and obscure. Data overload presents another erosion form. Observatories churn out vast data troves. Contemporary broad-sky hunts yield petabytes yearly. Each frame packs millions of data points. Each point holds a reading. Handling this calls for automated flows. Code that spots features, gauges locations, computes brightnesses, matches records, compiles lists, and marks oddities. These systems operate non-stop, absorbing inputs and generating outputs. But swelling quantities tax the processors. Computation durations delays mount. Patterns emerge. Information piles up. A photo captured this evening could linger unexamined until the following day or even later. Once an irregularity is spotted, once an analyst reviews it and deems it worthy of pursuit, the target has already shifted position. The opportunity for observation slips away. We forfeit the ability to verify, to fine-tune the path, to evaluate the potential threat. Storage capacity poses yet another hurdle. It demands robust setups, drives, servers, climate controls, fail-safes, and duplicates. Everything comes at a price. As funding shrinks, capacity takes the hit. Legacy files end up shunted to sluggish formats. Retrieval from tapes that demand hours of effort. Should you require reanalysis of past visuals, or a hunt for some dim entity overlooked initially, patience is essential. Requests are filed. You linger while tapes mount, data migrates, computations finish. Weeks elapse, and the subject vanishes. Constant alertness demands ongoing care, extending beyond equipment to code, protocols, and accumulated wisdom. Programs harbor flaws. Workflows embed outdated premises. A cutoff established half a decade back may no longer suit. The heavens evolve. Urban glow intensifies. Orbital swarms proliferate. Streaks and bursts now clutter every frame. The system marks them as outliers. Backlogs swell with bogus alerts. Genuine oddities sink beneath the noise. Tweaking that cutoff isn't straightforward. Dial it too far, and true finds evade detection. Ease it insufficiently, and the chaff persists. Personnel must oversee the workflow, adjust settings, validate outputs. Those individuals demand deep knowledge, hands-on familiarity, and organizational lore. Observers step away into retirement. Technicians advance elsewhere. The architects of the setup, attuned to its eccentricities, aware of vulnerabilities, mindful of past rationales, they depart. Records aid, yet fall short of fullness. Nuances fade. Fresh recruits arrive. They grasp the framework, but lack profound insight. The gut feel honed over seasons eludes them. Errors occur. Settings shift sans grasp of ripple effects. Alignment data updates amiss. Prior assumptions, once debated and dismissed, resurface unchallenged. The incoming group lacks context. Cycles of prior missteps recur. Efficiency erodes from peak. Identification efficiency wanes. Awareness dawns only through after-the-fact audits revealing overlooked captures the scope should have nabbed. The likeness to maturing minds is precise. Each begins keen, erodes subtly, dulls acuity, overlooks cues. Each calls for deliberate upkeep to temper the slide. Each succumbs in the end, regardless of diligence. The remedy mirrors. Revamp, realign, modernize, swap worn parts for fresh. Mentor successors. Chronicle all. Foster enduring recall. Combat disorder across tiers. Aware victory proves fleeting, yet aiming to postpone the end just long enough to count. Stanford's team demonstrated that inhibiting age-linked proteins in rodents revived certain navigation recall. The treatment didn't revert elders to youth. It rendered them somewhat less aged. It curbed the downturn. It extended the window, such as upkeep's role for scopes. It won't revert to mint state. It tempers the wear. It secures duration. Duration to spot the subsequent R2, the unforeseen guest, the entity lurking in brightness or at detection's fringe. Duration counts as the prime asset. System breakdowns, oversight gaps, erosion triumphs. We squander duration. And forfeiting duration equates to forfeiting foresight on impending arrivals. Now, to conclude, we'll cover forthcoming steps, key monitors, advocacy points, and ties to APIS, the inbound asteroid slated for 2029. Segment 15, Worldwide Summary, Upcoming Focuses, and Pathway Outline. Should R2 serve as an alarm, this charts the path ahead. The comet nears perihelion on October 20th, 2025, at 0.26 Australian dollars. Merely 8 days remain. In that span, these actions are vital. Initially, orbital projections refresh. Monitor the course. Hone the path. Scan for influences. Vapor release generates extra pulse. Should the comet surge anew, expel unevenly, the path deviates. Marginally, yet perhaps crucially. Sustain tracking. Sustain honing. Shun the notion that the present model stands fixed. Next, spectral analysis and ranging. Composition intel on R2 is essential. Spectral scans reveal the envelope's makeup, venting vapors, molecular lineup. Ranging, should proximity allow and antennas align properly, might delineate the core, gauge dimensions, note spin, perhaps discern features. Beyond mere inquiry, makeup shapes conduct. Icy cores prone to bursts. Form influences it heightens the chances of the comet breaking apart. If the core consists of a loosely aggregated pile of debris bound only by feeble gravity, it could disintegrate entirely. Conversely, if it's a cohesive solid body, it ought to remain whole. Determining this is crucial. Next, pursue detailed imaging. Attempt to discern the structure of the nucleus. Seek out any signs of breakup. Should R2 have already divided, with components drifting apart, we must spot them immediately to chart their paths. Pieces separate gradually initially. Detecting them sooner allows for more accurate forecasts of their destinations. Additionally, track dust and rubble. Scan for comet tails. Watch for outbursts. Monitor for meteor activity. Ground-based cameras can pick up particles streaking into our atmosphere. Orbital detectors can gauge the influx of tiny meteoroids. If R2 is releasing material, if our planet is nearing a stream of debris, early alerts are vital. Just a handful of hours' notice suffices to safeguard satellites, angling their solar arrays sideways to minimize exposure. Moreover, simulate threats to spacecraft. The International Space Station circles at roughly 400 kilometers altitude. Other satellites span from low Earth orbits to geosynchronous heights of 36,000 kilometers. Each represents a possible victim. A concentrated flow of meteoroids elevates impact probabilities. The overall danger remains modest, yet modest is contextual. Suppose the normal particle rate stands at 1 per million cubic km per hour. A debris surge boosting it to 10 per million cubic km per hour marks a tenfold jump. Tiny counts, when scaled across vast spaces and extended durations, accumulate significantly. Calculate the particle density, assess the threats, and devise backup plans. Turning to governance and infrastructure, what must we insist upon from the organizations tasked with our safeguarding? Primarily, fund sunward observation systems. The majority of telescopes face outward, away from the sun, a logical choice. Solar brilliance overwhelms detectors, yet threats emerging from that solar glare stay hidden until they clear it. We require orbital observatories placed to peer toward the sun. Sun-facing tools capable of spotting comets and asteroids amid the luminosity. The SOHO and SWAN missions demonstrated this feasibility. We should expand such arrays, tailoring them to comet hunting across broader wavelengths. Furthermore, establish instant public information flows. Openness counters unfounded rumors. Prompt release of sightings, live updates to orbital paths, and straightforward reporting of margins of error build confidence. Speculation fades once facts are out there. The Minor Planet Center and JPL offer this partially already, though their tools cater to experts. We need user-friendly displays, graphical overviews, and simple explanations. Render data approachable and comprehensible. Also, foster global teamwork. Observatories of the world, spanning time zones, viewing angles, and tech levels. A synchronized global web enables non-stop monitoring. As one site drops the target below its horizon, another assumes coverage. Standardized warning procedures. If a facility flags a danger, how swiftly does that intel propagate to peers? To leaders? Seconds count, as do minutes, hours, and days. Consider Apophis as a benchmark. Asteroid 99942 Apophis, around 340 meters across, will zip by nearer than geosynchronous orbits on April 13, 2029, just under 4 years from now. We've recognized Apophis since 2004, observing it for 21 years. Its path is mapped with pinpoint accuracy. We can specify its position on that date within kilometers. It won't collide with us. It'll skim at about 31,000 kilometers, tighter than certain satellites, yet harmless. We possess ample opportunity to ready gear, examine it during the encounter. Apophis exemplifies the foreseeable threat, the distant alert we can observe unfolding gradually. R2 embodies the reverse: erratic, belatedly spotted, orbit in doubt, makeup obscure, breakup a real possibility. R2 alarms hazard experts not for an imminent strike, but because detection nearly escaped us. And similar cases lurk out there. Ones we've overlooked. Ones that will blindside us until the 11th hour. The gap between Apophis and R2 boils down to timing. Apophis afforded decades. R2 offered mere weeks. In planetary protection, time reigns supreme. Time for scrutiny. Time to hone predictions. Time to weigh responses. Time to intervene. Exhaust that clock, and choices vanish. You're stuck observing, crossing fingers that the calculations prove solid, that error bars don't tilt adversely, that no shards veer into Earth-impacting paths. Foreseeable giants draw scrutiny. Apophis will undergo intensive probing. Telescopes will converge on it. Radars will bombard it with signals. A lone close approach will yield asteroid insights surpassing years of remote gazes. That's progress. But peril stems from the stealthy arrivals. Diminutive, swift, unforeseen. The wild cards, those concealed in solar dazzle, emerging from blind spots. Unexpected trajectories, those that flare up unexpectedly once we've glanced elsewhere. They're the kind that take us by surprise. The cosmos isn't out to destroy us, nor is it working to protect us. It's utterly neutral. Bodies hurtle across the void driven by gravitational pull and inertia. Occasionally, they intersect our trajectory. The majority veer clear, while a few make contact. The pattern follows probability, chaotic in the near term, but foreseeable across eons. We find ourselves in a narrow epoch where collisions are infrequent enough to allow societies to flourish, yet frequent enough to demand constant vigilance. The Chicxulub object that wiped out the dinosaurs slammed into Earth 66 million years back. Measuring 10 kilometers in diameter, hurtling at 20 kilometers per second, it unleashed power rivaling billions of atomic bombs. It carved out a 200 km wide scar. It hurled material high into the upper atmosphere. It shrouded the planet in gloom. It closed a chapter in life's history. Something similar could recur. Not right now, not soon, likely not in our era. But someday, the real issue boils down to this. Will we spot it in advance? Will we have moments to act? Or have we prepared the infrastructure, innovated the tools, prepared the experts, and aligned the organizations for an effective countermeasure? Or will we mirror the dinosaurs, oblivious right up to the moment the heavens ignite? R2 won't trigger that catastrophe. It's minuscule, distant, and meticulously monitored. Yet it serves as an examination. An evaluation of our tracking networks, our information-sharing protocols, our capacity to face the unknown with composure rather than frenzy. Up to now, we're succeeding. The comet's path is under observation. Its trajectory is being fine-tuned. The potential dangers are being relayed clearly. There's no widespread alarm, nor should there be. Instead, we ought to focus beyond the drama, beyond the media frenzy, beyond the wild speculations, the pessimists, or the sensationalists. Zero in on the weaknesses, the overlooked areas, the missed detections, the bureaucratic hurdles, the oversights stemming from misguided focus, flawed timing, or inadequate equipment. These represent the takeaways. These are the essentials, Observe the heavens. Push for superior monitoring setups. Challenge the stories we hear. Remain inquisitive. Remain doubtful. The universe brims with marvels and perils alike. Usually, the marvels pose no threat as we savor them. But the perils don't herald their arrival. They don't seek approval. They simply show up. And in those instants, the sole barrier between humanity and oblivion lies in the effectiveness of our early warning mechanisms and the swiftness of our countermeasures. Just 8 days from its nearest pass. Our two approaches. The data assures us of safety, but data offers estimates, not absolutes. Odds clad in formulas and likelihoods can still catch us unaware. That's precisely why we monitor. That's why we compute. That's why we construct observatories, educate stargazers, support scouting missions, and foster global partnerships. The other option, ignorance, is worse than the threats out there. The vastness isn't barren. It's cluttered with rubble, shards, transients, nomads. The bulk glide by without incident. A portion doesn't. R2 underscores that our cosmic locale isn't serene, that the orbital bustle is genuine, that the danger, though minimal, never vanishes entirely, and that alertness isn't overreaction. It's essential for endurance. Keep your eyes on it.